Hi everyone, welcome back to Chem Help ASAP. In this video, we are going to be discussing the reaction quotient and equilibrium. Let's get started. What is a reaction quotient? First, we symbolize it with a capital Q, and I do want to point out that if you have done thermodynamics, you have seen Q before, but that was a lowercase q. This is different. This is a reaction quotient, uppercase Q. So just watch those cases to know what kind of Q you are dealing with. The reaction quotient, uppercase Q, is a way to determine if a reaction is at equilibrium, and if it is not, which way the reaction will shift to reach equilibrium. When calculating Q, we're going to use initial concentrations. This is why, again, we specify that this is Q and not K. Remember, K must always be calculated with equilibrium concentrations or pressures. If we don't know if it's at equilibrium, we have to first calculate Q. So we can have three different scenarios here. Our first scenario, and our simplest, is Q is equal to KEQ. When Q and KEQ are the same, the system is at equilibrium. But of course, that's not always true. So let's look at a second scenario. Q is less than KEQ. Remember, your Ks are products over reactants. So if Q is less than KEQ, it means you have too much reactants and you need more products. So you need to form more products. The reaction will shift to the right to form those more products to again get to the situation where Q equals K and you're at equilibrium. Which brings us to scenario 3, which is of course the opposite of scenario 2. Q is greater than KEQ. Again, remembering that KEQ is products over reactants. In this case, the amount of products is too large and the amount of reactants needs to increase. So to increase reactants, the reaction is going to shift to the left to reach equilibrium. So we're using a calculation of Q to compare with our K to see first if we're at equilibrium, and then if we're not, which way are we going to shift to reach equilibrium. So let's look at an example. Consider the following reaction. We have a balanced chemical equation and equilibrium. Initially, the concentration of PCl5 is 0.56 molar, PCl3 is 0.789 molar, and chlorine is 0.125 molar. Is the system at equilibrium? If not, which way will the system shift? And we're given the KEQ for this reaction as being 0.225. So to know if we're at equilibrium and if not, which way we need to shift, we're going to calculate Q. So what is the equation or what is the expression for Q? It's actually the same as KEQ. So if we're writing KEQ for this equation, here is our expression for KEQ. It means that our Q looks exactly the same, except we specify that this is Q because we don't know yet if it is at equilibrium. So what we're going to do is we're going to take this expression for Q and we're going to plug in all of our initial concentrations and see what we get. So here's Q, we've plugged in all of our concentrations and we calculate Q to be 0.176. This is not the same as KEQ, so right away we can say this is not at equilibrium. Okay, so which way will the system shift? Well, we have to say, is Q bigger than K or is Q smaller than K? Well, 0.176 is definitely smaller than 0.225, so Q is less than K, which means we are going to shift right to make more products. Let's do one more example with Q. So we have a new system here. We've got hydrogen and nitrogen reacting to form ammonia, again in equilibrium, and everything is balanced. So determine if the system is at equilibrium. If it is not, specify which way the system will shift. And initially the pressure of hydrogen is 1.05, nitrogen is 0.978, and ammonia is 1.37. And we are given the KEQ of this reaction as 1.38. We write Q the same way we're going to write our KEQ. So here's our expression for KEQ. Q is exactly the same, except again, we specify that this is Q because we do not know if it is at equilibrium. So we are going to plug in all of our initial pressures here to calculate Q, and we get Q equals 1.66. So already these numbers are not equal, so we know it is not at equilibrium, but now we need to compare. Is it bigger or smaller to know which way it's going to shift? Well, 1.66 is definitely bigger than 1.38, so our Q is greater than K, which means our equilibrium is going to shift left. We're going to make more reactants. One thing I want to reiterate in this is when you're calculating Q, very often your problem will say these pressures or concentrations are given either initially or at some point in the reaction, and you don't know if they're at equilibrium. Remember, if you're going to be calculating a K, a KEQ, a KC, a KP, all of those amounts need to be at equilibrium. So if you don't know you're calculating a Q, you're not calculating a K. I hope you found this video helpful, and thanks so much for watching.